Today we're diving into something that feels like it's pulled straight from a sci-fi movie, electromagnetic cannons. Seriously, just think about it. Launching things at unbelievable speeds, not with gunpowder and explosions, but with the pure, invisible force of magnetism. So how on earth does that actually work? Let's get into it. All right, to really get what makes this tech so different, you gotta look at what we've been using for centuries. A normal firearm. It's all about chemistry. It's a controlled chemical explosion. And while that's powerful, the laws of chemistry put a hard cap on how fast you can go. An electromagnetic cannon, though, it just throws that rulebook out the window. It ditches chemistry entirely for raw physics, using magnetic fields to hit speeds that gunpowder just can't dream of. So, what is an electromagnetic cannon at its core? Well, it's basically any launcher that takes a whole bunch of stored electrical energy. Think of a massive bank of batteries or capacitors and converts it straight into motion, into kinetic energy. There's no bang, no chemical reaction, just this huge, almost silent wave of force. Okay, so how do you actually turn electricity into that kind of incredible motion? Well, it all comes down to a fundamental secret of the universe, a little principle from physics called the Lorentz force. This is the magic ingredient. The idea behind the Lorentz force is actually way simpler than it sounds. It's just the basic rule that says when you have electricity and magnetism in the same place, they interact. So if you run an electric current through a magnetic field, that field is going to push on it or pull on it. And that simple push is the engine that drives every single one of these launchers. And here's what that looks like in the language of physics. Now, don't worry, there's not going to be a test later. Let's just break it down real quick. The force, that's F, that's the push we want, is what you get when you run a current, I, through a conductor of a certain length, L, that happens to be sitting inside a magnetic field, B. You make the current stronger, you get more force. You make the magnetic field stronger, you get more force. It's that direct. So, let's picture what that formula actually does. It's this beautiful, powerful three-step process. First, you get an electric current flowing through something that conducts electricity. Second, you put that conductor inside a magnetic field. And third, bam, the Lorentz force just takes over, creating this massive push that sends the conductor flying forward. That's it. That's the whole principle right there. So, now that we get the basic force, let's meet the two main ways engineers have actually managed to build launchers with it. Think of them as two different contenders in the same weight class. First up, we've got the one you've probably heard of, the celebrity of the EM launcher world. This is the brute force, raw power member of the family, the railgun. Okay, so how does this beast work? Picture two long, parallel metal rails. You blast a huge pulse of electricity up one rail. The current then jumps across the projectile itself, which also has to be conductive, and then it flows all the way back down the second rail. That completes a circuit, right? And doing that creates this ridiculously intense magnetic field between the two rails, and that field exerts an absolutely massive Lorentz force on the projectile, kicking it down the rails and out the other end with just insane acceleration. And what do you get from all that raw force? You get speeds that are just hard to wrap your head around. We are talking Mach 6 and up. That's over 6 times the speed of sound. But, and this is a big but, that incredible speed comes at a serious cost. The insane heat and electrical current actually create plasma that literally tears the rails apart over time. It just shreds them. This rail erosion is the railgun's Achilles heel. That, and the fact that it needs a truly mind-boggling amount of power for every single shot. So, if the railgun is the sledgehammer of the group, our second type is much more of a precision instrument. Let's talk about the coilgun, which you might also hear called a Gauss cannon. It takes a totally different approach. A coilgun works in a completely opposite way. Instead of pushing the projectile from behind, it pulls it from the front. The barrel is lined with a whole series of electromagnetic coils. The first coil flicks on, creating a magnetic field that yanks the projectile forward. Now, here's the clever part. Right before the projectile gets to the center of that coil, the coil switches off, and the next coil in line switches on, continuing to pull it. It's like a magnetic relay race, with each coil passing the projectile to the next one, making it go faster and faster down the barrel. And this design has some huge advantages. Since the projectile never actually touches anything, there's no physical wear and tear, no erosion at all. That makes it way more durable and efficient. The trade-off? Well, coilguns usually can't hit those same face-melting speeds that railguns can. So let's just put them side by side for a second. You can really see the core difference here, right? The railgun is all about raw, brute force speed, but it tears itself apart in the process. The coilgun is the more elegant, efficient, and long-lasting design. It's really two totally different ways of thinking about the same problem.
So whether you're pushing with a railgun or pulling with a coil gun, both of these designs slam headfirst into the exact same gigantic fundamental problem, and that is the immense power problem.
The amount of energy needed for this stuff is just staggering. This isn't something you can just plug into a wall socket. We're talking about megawatts of power. That's enough energy to power a small town. And all of it has to be dumped into the launcher in a tiny fraction of a second, for just one shot. So where do you even get that kind of instant power? Well, you need really specialized gear, things like huge banks of capacitors that can store up a massive charge and then release it all at once, or these things called compulsators, which are basically heavy spinning flywheels that can generate one single massive pulse of electricity. Just figuring out the power supply is a monster of an engineering challenge all on its own. All right, we've gone over the science, the two main designs, and the single biggest problem. So where does all this leave us? What does the actual future of this amazing technology look like? Well, the reason people are pouring so much research into this is because the payoff could be huge. Imagine a weapon that doesn't need any dangerous explosive chemicals, one that can hit speeds gunpowder could never touch. And you could precisely control the speed of every shot with electronics. When you add in a much longer lifespan for the weapon itself, you can see why this is kind of a holy grail for engineers. But let's be realistic. We are a long way from perfect here. The hurdles are still massive. The power requirements mean you need a huge, heavy power supply. All that energy creates a ton of heat you have to get rid of somehow. And for railguns, that core problem of the rails destroying themselves is still the #1 thing holding them back. So where might we actually see this tech pop up first? The possibilities are really cool and pretty diverse. For the military, the obvious one is long-range cannons on ships. But there are amazing peaceful uses too, like using a giant launcher to help fling satellites into space, or using them in labs to test how materials hold up at insane speeds. It's even a tool for scientists doing basic research into plasma. And all of this really boils down to one big question. As our engineers get better and better at solving these huge problems of power and cooling and durability, are we looking at a future where our most powerful tools for defense and maybe even space travel are powered not by gunpowder, but by magnets? Now that is something to think about.